Hello everyone, welcome to Dakshana e-classroom programs. In last lecture, we discussed about thermal stress. We saw how a thermal stress is developed, when it is developed, and how we calculate thermal stress and thermal strain. And then we started talking about viscosity. Viscosity is basically a property of fluid. It can be either liquid and gas. So mainly we focus, when we are talking about viscosity, our focus is primarily only on liquids. We talk little bit about gases also. So in last lecture we understood what is exactly viscosity. So just like whenever two solid bodies are there and their surfaces are rough and they are in contact and some relative motion is involved, so the one body opposes the relative motion of other body, and this we call as like because of friction, or the force, that opposing force is termed as friction, is it? Or the property of the surface is basically roughness, because of that it acts. Similarly, when fluid molecules, fluid particles or liquid particles move relative to another particle, or that we define in terms of basically layer. So when one layer of fluid move relative to the other layer, then these fluid layer also have property to oppose their relative motion. So one layer of fluid has the property to oppose the relative motion of other layer, and this property we define as viscosity, right? So in last lecture I told you why that, what is the cause, what is the reason for having this property. So in liquid, viscosity is the result of cohesive force between the molecules of same medium, is it? That is the cohesive force is the reason for the viscosity. Similarly, in case of gases, the viscosity is not because of the cohesive force, it's because of the diffusion process. So that's why when we talked about the variation of or dependency of viscosity on different factors like on temperature and pressure, then it varies in different manner for gases and liquid. For liquid we saw pressure increases, viscosity increases, except water. For in case of water, the relation is exactly opposite. Pressure increases, viscosity decreases. In case of gases, it's almost independent of pressure. So viscosity of gases does not depend, but on temperature, yes, viscosity of temperature increases as temperature increases, because diffusion will increase. And for liquids, it's inversely related. Temperature increases, so viscosity of liquids decreases. So that is all we few things we talked about viscosity. Next things comes is okay, we understood viscosity. Viscosity means it's a property of liquid by virtue of which the relative motion between the layers of liquid is opposed, is it? We understood the reason also, but this opposing force, first thing is defined as viscous force, and next thing is comes can we calculate that viscous force? And yes, it can be done. And exactly on what factors, on what parameters that viscous force depends, let's see that. That comes under, we will study that under Newton's law of viscosity. So first thing is, let me define viscous force. Is it? So you can write, due to viscosity, the relative motion of one layer of liquid is opposed by the other layer in contact, right? Because of viscosity, this opposing force is called viscous force. Okay, so this we understood that if let's suppose this is a surface which is at rest, and on this fluid is flowing in these layers, is it? So the layer motion of one layer, so if it is having high velocity, velocity of next layer will keep on decreasing, so on. So this is all because of the opposing, the viscous force, or because of viscosity, the motion of this layer is opposed by the motion of lower layer, is it? That is what exactly happened. This force opposing means like some force will be applied. That force we define as viscous force. Is it? So here next point is, let's calculate that viscous force, and for that I will be like discussing in terms of Newton's law of viscosity. So to calculate that we need to define few more things. Let me first tell you that is what is, so that is called velocity gradient. Because the viscous force, is it, depends on these parameters. So that's why let me first tell you what is the velocity gradient. So here you can see this layer exactly in contact with the bottom or like stationary surface will have almost zero velocity. As you are going up, is it, so as we are going up, let's say distance y from this surface, and I'm considering this layer of thickness, let's say dy. Okay, so this is your surface AB, this is layer CD, and let's say the next layer is EF. Is it? So let me say the velocity of this is having some v plus dv, and this is having velocity v. So let consider here, let consider a layer of liquid CD at distance y from stationary okay surface AB. Is it? Liquid layer CD, or you can write at a distance y from, and having speed, let's say v. Is it? Or you can say velocity also. And the next layer at distance y plus dy. Is it? Next layer, I will write next layer, that is a EF at distance y plus dy and having velocity of v plus dv. So now you can see actually as you are going up, is it, from the stationary or bottom fixed surface, you will see the velocity will keep on increasing. The layer of fluid velocity will keep on increasing. So here we define the change in velocity divided by, like, as if I'm moving by dy amount, then exactly what will be the change in velocity. So that change in velocity with respect to change in distance from this stationary surface is defined as velocity gradient. So velocity gradient, it is defined as the ratio of change in velocity of layer with respect to, you will write change in its distance from stationary bottom layer or fixed surface. So velocity gradient, let me write Vg, this is equal to dv. You can check it from here for CD to EF. So the change in velocity delta v, you will write this is v plus dv minus v divided by y plus dy minus y. So this is equal to divided by delta y. So velocity gradient comes out to be dv by dy. This quantity is called as velocity gradient. So I hope this term should be clear. It's simple thing. We know actually if this is the fixed bottom surface, the liquid layer which will be in contact with this fixed surface will be having like almost zero velocity. As you are going up, the layers, is it, will have some velocity, and that will be like increasing. So the layer which is at like highest distance from this fixed surface will be having largest velocity, and the next lower layer will have smaller, 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 so on. So as we are going at the distance y or y plus dy, the velocity is changing, is it? So the change in velocity divided by the change in distance from this fixed bottom surface, this ratio is defined as velocity gradient. Okay, so now let me calculate this viscous force now. So we understood this term, that is velocity gradient. Okay, so now consider here, this is a fixed bottom surface and fluid is flowing or liquid is flowing in layers, and let's say the fluid, the liquid which I am considering is having, this is the surface, top surface. So this is having, A is the area of surface, is it, or layer of this fluid. So that is A. Now as we are going from y to y plus dy, its velocity is changing from v to v plus dy. So I can write velocity gradient will be equal to simply what? Velocity gradient here, that will be equal to dv by dy. Okay, now we are interested in calculating the viscous force acting on one of the layer. So viscous force acting on the fluid layer. Okay, so we like, this is all result of Newton's law of viscosity. He did a lot of experiment, and from there he observed that exactly on what factor, on what parameters this viscous force depends, is it? Just like the case we know in case of friction, friction force depends on what things? First thing is the surface in contact, means that is basically your coefficient of viscosity depends on the nature of contacting surfaces. Next thing is the normal reaction. Beside that, it doesn't depend on anything else, right? So exactly same manner, does viscosity also depends only on same parameter, or it's something little bit different? It's little bit different, and let me tell you what is that, exactly on what factors it depends. So viscous force acting on the layer, so it is all experimental result observed, and then the result we are going to study here. So it is the result says the viscous force is directly proportional to the velocity gradient. If velocity gradient is high, high viscous force will be acting on the layer. Viscous force also depends on the area or surface area of layer in contact, is it? Surface area of layer. Okay, so these are two parameters, and then combining these I can write viscous force is directly proportional to area multiplied by dv by dy, and this proportionality constant is calculated, and this implies this is replaced by eta, this a into dv by dy. This eta is called coefficient of viscosity. This negative sign is showing it will be resistive, it will be opposing force, right? Negative sign means it will be like opposing, it will oppose the motion of layer, and exactly in which direction it will act. So you can understand, if let's say this is layer 1, this is 2, 3, 4, 5, 6, is it? So when I am, let's say, calculating at layer, this is a 4, then on layer 4 due to layer 3, is it, the force on layer 4 will be in this direction. So means on upper layer the force will be opposing, so the motion of this layer is in forward direction, then the force will be acting backward and tangential, is it? So this force F will be tangential to layer, or you can write in opposite direction of velocity of layer. So just like the way if two blocks are moving, friction is acting, then on one block it will be like in forward direction, another block it will be in backward direction, right? So exactly similar situation happen here also. So if on, like, let's say this is like I am considering this is just one layer, this is another layer, these two are, so on upper layer force will be in backward direction, on lower layer it will be in forward direction, and the force is given by F is equal to eta A dV by dy. The dV by dy you already understood, A area of layer in contact, and this eta is called coefficient of viscosity, right? And for this we measure the viscosity coefficient, the unit I told yesterday, unit for eta, this is either decapoise or Poiseuille, is it? These are SI units, and CGS unit is only poise, and the relation between decapoise and Poiseuille, so 1 decapoise or 1 Poiseuille equal to 10 poise. This is the relation between the units. Eta is coefficient of viscosity, negative will be negative sign implies it will be opposing force. It will oppose the relative motion of upper layer with respect to bottom layer. It will oppose the relative motion of upper layer with respect to lower layer. So this is how, like, we finally got this expression. This is, you can say, called Newton's law of viscosity, and this is your viscous force, which depends on eta. Eta is the fluid property. Eta will be depending on what? Depends on pressure, temperature and fluid. So when you are changing the pressure, temperature and fluid, then only your eta will be changing. So eta is the measurement of that, like viscosity. We measure it in terms of coefficient of viscosity. So it will be like depending on, so you can write here eta, property of fluid, and depends on temperature, pressure, or related to density also. That I already told you yesterday, how it exactly varies. So this finally, and we are getting, so now we are in position to calculate the viscous force acting on one layer, is it, by the lower layer, and that is given by this formula. We call this is Newton's law of viscosity. Simply F viscous force is minus of eta times A. A is the area of this layer, so this you can say the area of this layer, and dV by dy is the velocity gradient. Okay, let's see some basic application here. So a man is rowing a boat with constant velocity v0 in a river. The contact area of boat is, the area of contact of the boat which is in contact with the water is A, and the coefficient of viscosity is also given as eta. The depth of the river is d, and find the force required to row the boat. So first thing is, like, the boat is moving with constant velocity, so I can say the fluid in contact with this will be also having same velocity v0, and definitely because depth is d, so here the velocity of the fluid will be, you can write say 0. So if I say like velocity gradient, then what will be velocity gradient? So here at this height velocity is v0 minus, here it's 0 divided by y, it's d minus 0, so v0 by d is the velocity gradient. Clear? And the coefficient of viscosity is, so here this man has to apply some force, so let's say F, and backwards some viscous force will be acting, so we can write F minus F viscous should be equal to what? Mass of the boat multiplied by some acceleration, but it's mentioned it's moving with rowing with constant velocity, so definitely A will be equal to 0. So that means the force required, is it, by the man like should be equal to simply viscous force, and that is equal to viscous force we know eta. Area of a boat in contact is A multiplied with velocity gradient, that is dv by dy, and this eta A dv by dy velocity gradient is v naught by b. So this is the force required for to row the boat is given by this. So I hope you are clear with this simple thing. Velocity gradient, you need to understand what exactly is happening. The man is rowing the boat, viscous force will be acting upward, it will oppose. To counter that, so that the boat is moving with constant velocity, man has to constantly apply some force, and that is given by this force, that is equal to the viscous force. Let's see the next problem. A cubical box of side 2 meter and mass 20 kg. So here mass of the box is 20 kg and the side is 2 meter and it's cubical box. Okay, and slide on inclined plane lubricated with oil of coefficient of viscosity. So eta is given as 1 by 10 poise. Okay, with a constant velocity of 10 meter per second. So this is moving with constant velocity of 10 meter per second. Taking g is equal to 10 meter per second square, find out thickness of the layer. Now you need to keep some points here is that this block is sliding on inclined plane. So if let's suppose there is no viscous force, then it will have some acceleration, that is g sine theta. So that is because of mg will be acting downward like this way. So one component will be on this, that is mg sine theta force. So this is the force. Now because it's moving with constant velocity, that means the viscous force is exactly equal to how much? This force, mg sine theta. So viscous force, F viscous force must be balancing this mg sine theta. Then only it's possible for the cubical block to slide with constant velocity. And then for calculating viscous force, you can see the fluid in contact lubricant here will have same velocity v, and here it will have zero velocity. So velocity gradient can be written as velocity gradient will be equal to what? If I say the thickness of the lubricant is T, then that will be equal to V minus 0 divided by T minus 0, that is V by T, where T is the thickness of lubricant, thickness of oil layer. Okay, so we understood this. Then what will be the viscous force acting on this block? So for that, eta A, area into velocity gradient dv by dy. Eta we know already, let's say eta. Area will be equal to what? It's cubical box, so area I can write area will be equal to 2 into 2, 4 meter square. So we got area, so into A into velocity gradient is V divided by T. Now this force must be equal to mg sine theta to balance and so that the block is moving with constant velocity, and this implies eta is 1 by, okay, remaining things I am taking all in terms of SI units. So this poise is a CGS unit. So SI unit will be like deca poise. Then eta will be equal to what? So it will be like eta is 1 by 10. So in SI unit poisely it will be 1. So eta is equal to 1 deca poise. Deca poise. Right? That will be 10 into poise. So 10 by 10 it will be equal to simply 1. So then mg 20, g 10, sine 30 1 by 2 equal to eta 1 into area 4 into velocity 10 divided by thickness t. And then simplifying it, we are getting 10 gets cancelled. T is coming out to be 4 divided by, this is 10. Let me just check the things. Eta A dv by dt, yes, and this is m g sine theta. Yes, so we are getting thickness is equal to 4 by 10 centimeter. That is like it will be equal to 4 by 10 meter. So 0.4 meter. That's coming out to like quite a large thickness. Let me just check the result. Okay, just wait, I did one mistake. So eta, this is given as 1 by 10 poise, and let me write it here. We know actually 1 poise is equal to 1 by 10 decapoise. So actually here eta will be equal to 1 by 100 decapoise. I did mistake here. So then taking it will be like 1 by 100, and then substituting it will be like 1 by 100 multiplied by this, so will be 100, then it will comes out to be simply 4 mm. This is the correct statement, correct answer. So the thickness of the lubricant here or oil will be 4 mm. So these are basic application of Newton's law of viscosity or calculation of viscous force. Let's continue. So we are actually from the beginning, the discussion of viscosity, we are talking about parallelly viscous force and friction force, is it? So they are some similarity and some differences between them. Sometimes these are like important, you will be required in some logical questions, so you should keep those things in your mind. So let me mention all the similarities and all the differences between the viscous force and solid friction. So viscous force and first let me talk about similarities. So viscous force and friction force, both are basically opposing the relative motion, is it? So both opposes the relative motion. Viscous force between the layers of the fluid and friction force between the two bodies in contact. Both are both comes into play whenever there is some relative motion. So that you must have even studied. In case of friction also, if there is no relative motion or no tendency of relative motion, no friction will be acting, is it? And similarly in case of viscous force, if velocity gradient is 0, viscous force will be also 0. So both comes to play, comes into existence only whenever there is relative motion between layers of the fluid or between these two solid bodies in contact. Both are due to the molecular attraction. I told you in case of liquid, it's because of cohesive force, and in solid also, one of the reason for friction force is the attraction between the molecules or molecular attraction. Similarly, the difference between both of them, here we saw that friction, viscous force depends on the area of layer in contact, but friction force, it does not depend on the area of contact. Similarly, next is viscous force depends on the velocity gradient, but friction force is independent of velocity gradient. And the third one is the normal relation. Viscous force is independent of normal relation between two layers, but friction force is directly proportional to the normal relation between two solid contacting bodies, is it? So these are like few points about similarity and difference between viscous force and friction force or solid friction. Let's see more about viscosity now. So it's more of like its application, that is Stokes Law and terminal velocity, both are important. Okay, so by this time we are clear with the viscous force, and we also understood the difference between viscous force and friction force. So viscous force means whenever some fluid is flowing and there is some relative motion between the layers of the fluid, then relative motion is opposed by the force, we call that viscous force. Let's talk about next thing. Like, let's say fluid is there and some object, some solid body is dropped in it, or you can say a solid body or one body is passing through the fluid. What will happen in that case? Do you think that the fluid, the liquid, will oppose the motion of this solid body also? I think the answer is straightforward. You must be even agreeing with that, and yes, it is right actually. So in that case means, like, let's consider this is the container which is filled with some fluid. Okay, let's fill it up to here, and one body is passing through this. So it's moving with some, let's say we have dropped, so it's moving at some point of time, it has some velocity v. So what will happen? The fluid which is in contact with this body will be also moving downward with the same velocity almost, and the fluid which is away from the body will be almost at rest. So we can see there is some velocity gradient, and definitely viscosity will be there, is it? Means sort of like you can understand this fluid, this solid body will cause the relative motion between different layers of the fluid, and that will ultimately give rise to what? Viscous force. So viscous force also act on a solid body when it is passing through a liquid. So viscous force also act on a body passing through a fluid, or you can say liquid. right? So when a body is passing through the liquid, then also the body will experience some viscous force. And yes, so next comes is like, what will be that viscous force? So the question is, because the shape of the body can be random, so we cannot generalize this calculation of viscous force on any random body. But Stokes was one scientist who derived the expression for the viscous force only for spherical bodies. Is it? So for any random shape body, it's not easy to calculate actually. We defined that Newton's law of viscous force, that was only when some layers is there, one plate is moving, then in that case on that plate or between the layer we can calculate the viscous force. Here some random body is moving through the fluid, it will be like, yes, calculatable, but it will be difficult. So here we study only for one special case, that is for spherical body. So when a spherical body, or you can say spherical body, passes through a liquid, the force, or I will say the viscous force acting on body was calculated by Stokes, and this we call as Stokes law, is it? And the relation we call of this viscous force is termed as Stokes law. So next thing is like, what is that relation, is it? So let's consider we have this solid spherical body. Now you must be clear, now our discussion is limited only up to spherical body, is it? Only spherical body. Right? So let's say this is a container filled with some fluid, and this is a spherical body whose radius is r. It's moving with some velocity v. Viscosity of fluid is eta. So eta viscosity or coefficient of viscosity of liquid, r radius of sphere or spherical body, v velocity with which it is moving, right? In this situation, this is all experimental. It was found by Stokes that viscous force acting on this spherical body is directly proportional to r, directly proportional to velocity, directly proportional to eta also, and cumulatively combining this directly eta r v, and this proportionality constant was calculated, and it comes out to be 6 pi eta r v, negative sign because it will be opposing. This relation is termed as Stokes law. So I hope you must be clear what is the Stokes law. Simple thing is, we understood simply viscosity. We define viscous force whenever some relative motion only between the different layers of the liquid is there. They will oppose, and we call that like opposing property of fluid, viscosity. The opposing force, viscous force. Next things come is that when some solid body or some other body is moving or passing through the fluid, then that solid body will be also opposed, or the motion of the solid body will be also opposed, or it will also experience some resistance force or some opposing force, and that is also like we call viscous force. Now the next thing is like, for any random shape body we have not calculated, and the expression for calculation of viscous force will not be also easy. So only the calculation was done for spherical body, and that relation, is it, we defined as Stokes law, and Stokes law derived it based on the experimental result, it's proportional to r. Like different experiments were done by changing the radius, by changing the speed, by changing the eta and so on. Then it was observed that exactly on what factors it is depending. So this is like, now here you can see if the body is moving downward, this will be an opposing force. So viscous force will be acting in which direction? This is viscous force. So you can see the viscous force will be acting in upward direction, viscous force, right? This relation is simply termed as Stokes law. Clear? Now let me tell you a few more interesting things about it actually. So you know actually raindrops, is it? This is all just about Stokes law. Remember this relation, it's quite important. It will be used a lot also. So next thing is, like, I'm just telling you a few interesting things actually, is it? So raindrops, everyone is familiar, and let's say the height of the raindrops in the sky, I would say it's falling like because normally the height of this cloud, it's quite large, but when raining is there, they comes a little bit down also. But just I'm not taking accurate data, just roughly let's say height of the cloud, is it, of clouds in the sky, let's say h, I'm taking it 5 kilometer, means 5000 meter. G will be almost 10 meter per second. So just imagine if the raindrop is falling from there, in acceleration G will be continuously acting, so it will be accelerating. So by the time it is reaching on the ground, can you just imagine how much speed it will be gaining, is it? So I can write v square minus u square is equal to 2a into s, that is 5000, right? 5000, 5 kilometer. I'm just taking simple, like even if it is falling from 5 kilometer, it's actually more than that, that's definitely. So I'm just taking, then it's coming out to be how much? 10 and 4. So v is equal to how much? It's basically 100 root 10, and that will be roughly 300, because root 10 will be something 3 point something, so it will be 300. I'm just taking it roughly 300 meter per second. Can you just imagine how big this is? And that you can also, v is equal to 300 multiplied by 18 by 5, so it will be like 6, this is 720 kilometer per hour. This is very large speed. Just imagine a raindrop striking with this much, it will be acting just like bullet actually. So what will be the situation if some person is standing in the like outside in the rain and that raindrops are falling with this much speed? That person will not be like surviving anymore. So then the thing is, mathematically if we are going, then this should be the condition. Raindrops should be hitting should be falling by at least 720 kilometer per hour speed. But actually let me tell you, this is definitely not, and that's why we can like hold our hand also in the like outside rain and we don't feel any pain, no problem is there, not much. So this is so then why, how all this happen actually? Because of viscous force. And that is like how you can imagine how important it is, how important role the viscous force is playing in the nature actually, because otherwise the survival of life on the planet, it would be like very difficult, at least for animals. Is it? Because most of the animals are simply roaming outside. We human beings can be even hiding ourselves inside the homes, we can survive, but animals, it will be like very difficult. So this speed is actually because it's not continuously accelerated up to this much distance, so that's why the velocity gained by the raindrops is actually not this, it's very small, it's maybe like around 10 kilometer per hour, 10 meter per second, 20 meter per second, 30 meter per second, only that much. So you can just imagine how small it is actually, right? And that's because of viscous force, is it? So there comes one more thing actually, like why it is not accelerating exactly and how that speed reduces. Let me tell you about that. So the idea should be like clear, because of the viscous force, it's opposing that, that's why it's not letting the allowing the velocity of the rains to be increasing continuously up to the point it's finally hitting the ground. So next comes is terminal velocity. Let me first explain you that concept. Okay, so next is terminal velocity. So just consider one imaginary concept, or you can just like hypothetical situation. So let's say I have one container filled with liquid of density. So rho or the sigma is the density of of liquid. Eta is the viscosity or coefficient of viscosity of the liquid filled in it. And this is a long tube which is having filled with liquid. A ball is dropped from the top with initial velocity. So you can write its initial velocity will be 0. And rho is the density of this ball, r is the radius. Now just imagine what will happen. Let's say some container is there filled with water, and in that we are dropping some ball, is it? So depending on like if rho is less than this sigma, this ball may be like moving upward, is it? So let me just right now for this moment to imagine it easily, I am considering this condition. So rho is greater than sigma. I will talk about that case also. If rho is less than sigma, what will happen in that case too. So now this is the simple situation. So in this situation, what will happen actually? Initially, you can see what will happen? Velocity will be 0. So there will be no viscous force, because viscous force by Stokes Law 6 pi eta RV, it will depends on velocity. Velocity 0 means viscous force 0. So but what will happen? Downward force mg will be acting on it, and one more thing actually here, buoyancy force will be also acting on it. Is it? So after some time, like because this condition is there, so that means already buoyancy force will be like still small, mg will be dominating, so it will be accelerating downward. Initially ball will be accelerating downward, right? So because of that, let's say after some time it has reached here, then it has some velocity v. Then in this situation, what will happen actually? Velocity v, downward force still mg is acting, upward force buoyancy force is acting, and because now it has attained some velocity, so viscous force will also start acting upward. Clear? Just simple, you can imagine. Now what will happen? Because initially ball's velocity is 0, so viscous force will be 0, is it? But as it's accelerating downward, so viscous force will be, I can write 6 pi eta rv, and it will be upward. Clear? So this will be the viscous force. Now here you can see, as your velocity increase, so this component viscous force will also keep on increasing, and buoyancy force, we know already, buoyancy force is equal to how much? It will be constant. So this is volume into density of liquid, that's sigma into g. So you can write 4 by 3 pi r cube multiplied by sigma into g. It will be constant simply, and the weight mg will be downward, that will be 4 by 3 pi r cube into rho into g. So this force will be downward and it will be constant, this force will be upward, it will be also constant, and you can say initially this mg will be dominating, that's why this force will be smaller, so the ball will accelerate. As it accelerates, its velocity will keep on increasing, and you can imagine here easily this viscous force will keep on increasing. So what is happening? Overall, you can see the acceleration of the ball downward is decreasing, is it? So that implies acceleration of ball, or is it spherical body will keep on decreasing, right? This is what happening. Total net acceleration downward is decreasing, and there is one possibility that this viscous force increases sufficiently such that these two upward force is exactly balancing the downward force mg, is it? So there arises one possibility or condition that on this ball downward force mg upward force, viscous and buoyancy force. So viscous plus buoyancy force minus mg is exactly cancelled. In this situation, net force acting on the body will be what? 0. So you can write F net will be 0. Acceleration of the body will become 0. What it means? Simple thing, that now the velocity of body will not change, right? And this velocity, it will be moving downward with some velocity v naught, or we can call it terminal velocity. So this constant velocity is simply termed as terminal velocity. That is what exactly happen in case of raindrops. Initially they accelerate up to some instant, up to some point. After that, upward viscous force plus buoyancy force balances exactly the downward mg force, and beyond that no further acceleration of raindrops is taking place. So the velocity of raindrops becomes constant. So even when they are falling like many kilometers, still the velocity remains constant. If there arises any situation like buoyancy force is increasing, means either upward for any of the upward force is increasing, then there is possibility that the raindrop might be decelerating. Otherwise, if they are moving with constant velocity, then in that case the velocity will remain constant. So in this situation, you can easily imagine there arises one condition when the net force acting on the ball becomes 0, is it acceleration becomes 0, then the body move with constant acceleration, moves with constant velocity. This constant velocity is termed as terminal velocity. So now we can calculate it easily. I hope everything making sense logically to everyone. So I don't think there is any point of any, there should not be any confusion in this simple thing initially, because this force is not able to balance this, that's why it's accelerating downward. Velocity initially will increase. After this time, like what will happen, this force will also start increasing. So there arises one condition that these things are exactly balanced. You can write mg minus fv minus fv equal to 0. That is exactly same thing. So after this moment of time, net force becomes 0, acceleration becomes 0, then the body move with constant velocity, and this constant velocity is termed as terminal velocity. Now we can even calculate what will be that terminal velocity. So this, what it implies, I can write mg downward force 4 by 3 pi r cube into rho into g must be equal to upward force 6 pi eta rv terminal plus 4 by 3 pi r cube into sigma. This is just wait, mg, and this is buoyancy force. Let me bring it this side, rearranging it, and then I'm getting 6 pi eta rv. I'm bringing this term this side and taking just swapping the terms. So then I'm taking 4 by 3 pi r cube common, then it will be what? Rho minus sigma multiplied by g, and then 1 r gets cancelled, so it will be r square. Pi gets cancelled, and so it will be 3, it will be 2. Just rearranging, v terminal is coming out to be 2 r square into g. This is rho minus sigma divided by, it will be 9 eta. This is the final expression for terminal velocity. So terminal velocity depends on g, that is actually constant, depends on the density of body, density of liquid, and it also inversely proportional to viscosity of the liquid, and directly proportional to the square of the radius. Is it square of the radius of spherical ball or body? So this is finally the expression, and we define this as terminal velocity. Okay, let's see some problem based on terminal velocity and its application. So consider here a drop of water of rate 0.0015 mm, means radius of the drop is 1.5 into 10 to the power minus 6 meter, is falling in air. Viscosity of air, eta air, is also given 1.8 into 10 to the power minus 5 kg per meter second. And what will be the terminal velocity of drop? Density of air can be neglected. So we know what is the formula of terminal velocity. It's like 2 by 9 r square g rho minus sigma divided by eta. Two simple constants. So let's substitute the value by 9. R is the radius of the drop, that is 1.5 into 10 to the power minus 6 whole square, into G is given as 9.8 multiplied by density of the ball, that is actually here drop, that will be like density of water 10 to the power 3 minus density of air medium, that is supposed to be neglected. This whole divided by eta. Eta is 1.8 into 10 to the power minus 5. So this is simple formula based problem. We can substitute the data and simplifying, doing the calculation, and we get it solving. It's 2.72 into 10 to the power minus 4 meter per second. This is the terminal velocity of this air drop, like water drop. See the next problem. So a spherical ball is moving with terminal velocity inside the liquid. Determine the relationship of heat loss with the radius of ball. So first thing is heat loss, and like heat loss will be because of which force, I mean like which will be the dissipating force here. So that you can say dissipating force here will be your viscous force, right? And what is that viscous force? We know it's by Stokes Law, 6 pi eta r into v will be the viscous force. And then what is the heat loss? Means rate of heat loss, we can write power, and power is equal to what? Force dot velocity, dot product of force into velocity. And because it's already mentioned ball is moving with the terminal velocity, that means terminal velocity will be equal to what? 2 by 9 r square into g rho minus sigma divided by eta. So now the power, and that due to the viscous force, and that is actually, this is the heat loss or rate of heat loss. This is also equal to rate of heat loss. So that can be written as simply force multiplied by viscous velocity, terminal velocity, simply substituting 6 pi eta rv multiplied by this, and this velocity will be also terminal velocity. So let me substitute, this will be v square is this, so that means 2 r square into g, this is rho minus sigma divided by 9 eta complete whole square. So it's simply asking the relationship of heat loss with the radius. So radius, it will be r, and it will be like here r square also, and that whole square. So the actual relationship of the heat loss will be, rate of heat loss will be that, and you can write from here P is directly proportional to r raised to power 5. So this is the answer to this problem. So things are easy, straightforward. You just need to remember these relations. This is from Stokes Law, and that is the formula of terminal velocity. Just substitute the values, we are getting straightforward answers. Okay, so the next problem here, we have a metallic sphere of 1.0 10 to the power minus 3 meter radius. This is basically metallic sphere of radius. This is radius of the sphere, and density of this is 10 to the power 4 kg per meter cube. Enter a tank of water after a free fall through a distance of h. In the Earth's gravitational field, if its velocity remains unchanged after entering water tank, determine the value of h. So the question it's saying is that, let's say here we have one water tank of, let's say, sufficient length, and it's filled up to here. And the ball, metallic ball, is dropped from some height, let's say h, is it? Before entering the water tank, it is traveling a height h, a distance h in the Earth's gravitational field. So it will be gaining some velocity here. Let's say the velocity here, that can be written under root 2gh if it is falling through a distance of h in the Earth's gravitational field. Now what is mentioned is that, like, once it is entering, immediately after that its velocity is not changing. That means, so it's moving with velocity, and that can be possible only when that point, the moment it is entering into the water, it's immediately, I mean like just before entering, it must attain the velocity equal to terminal velocity. Then only it is possible that velocity of metallic ball is not changing even when it is entering into the water. So means like, that means like we get the velocity of the ball, and then from this relation we can easily get the h. So let, like by using the data provided to us, let's calculate first the terminal velocity. So here all the information: radius of the ball is given as 10 to the power minus 3 meter, density of the ball is 10 to the power 4 kg per meter cube, and we know the terminal speed, it's given by 2 r square g rho minus sigma divided by 9 eta. So we have r already, rho is given, and it's falling in the tank of water, so means density sigma is 10 to the power 3 kg per meter cube, and then we need actually eta, and eta, density of water, viscosity of water is also given, so eta water is also given 10 to the power minus 3 Newton second meter square. So let me first substitute everything there and get the velocity or value of terminal speed. So it's 2 into r square, that will be like 10 to the power minus 6 multiplied by g, that means 10, and this rho is 10 to the power 4 minus 10 to the power 3, and this divided by 9 into eta is equal to 10 raised to power minus 3. We can simplify it, so 2 into 10 raised to power this is minus 6 into 10 into, this will be how much, I can take 10 raised to power 3 out, then it will be 9 divided by 9 into 10 raised to power minus 3. So this simply gone, and it's left 10 raised to power 6. This is, so it's coming out to be simply 20 meter per second. That is the terminal speed. That means just before entering the tank, the ball is attaining that much velocity, and that is equal to the terminal velocity. Then it's actually asking that from how much height the ball is actually dropped, is it? So this h is asked. Then we can write, so we got this terminal speed, this implies Vt is equal to under root 2gh, and this implies h is equal to Vt square divided by 2g. Let's just substitute the values. So it's 20 multiplied by 20 divided by 2 into g is 10, and solving it we are getting it's simply 20 meter. This is the answer to this problem. So I hope by this time you must be clear with the calculation part with the example based on terminal velocity and application of Stokes law. So this is all about your viscosity part. Let's continue from here onward in the next class. Thank you.